Hello everyone. Today we are going to look at a new type of mechanism called SNI, or internal nucleophilic substitution. This reaction occurs between thionyl chloride and an alcohol, and we learned that thionyl chloride reacts with alcohols to produce chlorides. Okay, I'm going to condense this mechanism into just a couple steps, even though it is actually many steps. This reaction begins with our alcohol attacking this partially positive sulfur. It's partially positive because it has many electronegative elements attached to it. Okay. And again, this is going to happen in multiple steps, but eventually the chloride is going to get kicked off, as is the proton on the oxygen. Okay, this leaves us with our intermediate, where all the magic happens. Oxygen is now bonded to sulfur, which has one chlorine, and a double bonded oxygen. The hydrogen and chlorine actually leave as HCl. Okay, and this is where this mechanism is different than other nucleophilic substitutions. Eventually, it's energetically favorable for this oxygen to break away from the carbon. When this happens, we end up with this: a carbocation, R, and this molecule. The oxygen is negative and R is positive, and it's important that we note their positions. This reaction, R and O, they could just react with each other and reverse this reaction. What will be more energetically favorable and will eventually happen is chlorine will attack R. Okay, when that happens, we'll end up getting an alkyl chloride. The important thing about this, unlike a typical SN2 reaction, is the location. This is not a backside attack. Because of just the orientation of the molecule, chlorine and oxygen are on the same side of R. Okay, so you can think of this as a same side attack. The resulting product, RCl, retains its original stereo conformation if this was a chiral center. We call this retention. Okay, so this reaction occurs with retention of chirality. The other product would have been SO2, which is a gas. Okay, so SNI reactions result in retention of chirality, and the reason is the nucleophile, Cl in this case, is attacking from the same side that O left from. Well, this reaction can occur a little bit differently if we add a substance called pyridine. What pyridine does is it reacts with the Cl on the SOCl2. Okay, if pyridine is present, this will not happen. Pyridine will actually replace the Cl. Kicking the Cl off, leaving us with a Cl minus floating around. And when pyridine kicks off the Cl minus is actually able to attack that R from the backside and give you a product that has inverted stereochemistry, as we learned that SN2 reactions do. Okay, and the pyridine also stabilizes that whole leaving group, allowing for this reaction to occur more easily. Okay, so just a quick summary. An alcohol reacts with SOCl2 to produce an alcohol, or sorry, a chloride. But it can also react with SOCl2 with pyridine included. They produce a chloride. So what's the difference? The difference is the stereochemistry. Okay, so the first reaction with no pyridine results in retention. When we have pyridine present, we get inversion of the stereochemistry. Okay, it's only relevant, of course, if R is a chiral center, but this allows for two different reactions with SOCl2, one proceeding through SN2 and the other proceeding through the SNI pathway. Okay? So you can see the full mechanism for pyridine reacting with SOCl2 in your book. Like I said, that retention mechanism is probably about 6 steps. I'm just trying to simplify it, but the main idea is the just intimate proximity of the two ions that force them to react from the same side. Okay, if you have any questions, please let me know on Google Classroom. Have a good one.